It's time for the 2019 midterm 1, or sorry, spring 2019 midterm 1 for MA 262. So let's just get going. Question 1. We are given this equation right here with an initial condition, and we're looking for y for t is equal to 3. Let's rewrite this a little bit. We have y prime multiplied by x squared plus 3 is equal to xy. Now, I actually have a lot of trouble with this still, seeing a separable equation when one exists. But what you should be able to notice, and in fact, I should really have this as dy dx because we're using the power of separation of variables, because what we should do is notice that our only function of y is over here, and it's, this whole equation is organized such that we can isolate it. So let's move some things around. Let's say dy dx multiplied by 1 over y, so we're dividing y over to the left side, is equal to x over x squared plus 3, dividing this term over to the right. Then if we multiply dx up here and rearrange this a little bit, this is dy, and then integrate both sides, we should be able to solve for y. We get ln y is equal to 1/2 ln x squared plus 3 plus c. That works, right? Yes, that looks good. That looks good to me. Okay, so we are not done yet because we'll need to write this explicitly in the form y equals in order to use these initial conditions. So let's take e raised to both sides here. That will give us y on our left side, and then we can rewrite that right side as c times 1/2 ln x squared plus 3, and we can further rewrite this as c times x squared plus 3 to the 1/2. And this, I'll write it as c0 because that kind of just looks like another parentheses. Okay, so now we have an explicit formula. We're told that y at 1 is equal to 8. I got to pull up the, there we go, the answer key. Y at 1 is equal to 8, so 8 is equal to c0 times 4 to the 1/2. That's just 2, and so c0 is equal to 4. So I'll replace that right up there, and we're evaluating y at 3. Y at 3 will be 4 times 12 to the 1/2, and that's not immediately clear as an answer choice, but if we rewrite root 12 as 2 times 2 times 3, we can bring a 2 out here, and we get 8 root 3, which is D for number 1, and that is correct. Question 2, for x greater than 0, what's the solution to this equation right here? Since we're given some really highly implicit answer choices over here, and since we have a parentheses off function here and then another parentheses off function multiplied by y prime, those are really your key indications that we're dealing with an exact differential equation. And an exact differential equation is one such that this function right here, the thing not multiplied by y prime, we'll call that m, we'll call this guy n, the thing multiplied by y prime. So an exact equation works such that we can find my, the partial derivative of m with respect to y, and that will always be equal to the partial derivative of n with respect to x. So let's test these two to see if that works out. I think it will. So the derivative of m with respect to y is 2 over x, and the derivative of n with respect to x is 2 over x. Would you look at that? So now all we need to do is take the integral of m, so 2y over x plus 2x dx, and then compare that with what we get when we take the integral of n, which is 2 ln x minus 3 dy. So what do we get here? We get 2 ln x times y plus x squared, and we're comparing that with 2y ln x minus 3y. So now what we do to form our real answer is note that, okay, we have overlap here and here, so we'll only count those terms once in our final answer, and then we have two unique terms that we'll also count separately. So I always explain that in a little bit of a confusing way, but hopefully it does make sense that we can just write down 2y ln x minus 3y plus x squared is equal to some constant c. We can't forget that in the end. And so what you should be able to do at this point is to walk back and see that the partial derivative of this with respect to x will give you exactly our function m, and our partial derivative with respect to y will give us that function n. And that's how you know that you've really done the correct thing the whole way through. Where is our answer choice? Looks like A works out pretty well, and the answer key agrees. Question 3, on the domain x greater than 0, consider this equation. What is its general solution? So this guy is not going to be exact. I can tell you that much, but let's rearrange it a little bit. We can write this as x minus 8y plus 4x y prime is equal to 0. Let's move these guys over to the other side. We get 8y minus x, and then divide out 4x. We can further rewrite this as y prime is equal to 2y over x minus 1/4. And this is great. Whenever you see a y over x directly like this, that means that we can apply this substitution. We can say that v is equal to y over x, and that our dy dx will become dv dx times x plus v. So let's perform that substitution. dv dx times x plus v is equal to 2v minus 1/4. Subtracting a v from both sides gives us that, and then we can separate our variables here, and we should be pretty close to an answer. So moving things around a little bit, we will have 1 over v minus 1/4 dv is equal to 1 over x dx. Integrating both sides, we get ln v minus 1/4 is equal to ln x plus c. Taking e raised to both of these sides, we can take out these natural logs. That will give us v minus 1/4 is equal to c times x, because we could bring this c down as just some other constant here, and then e to the ln x will just give us x. So this is cx. Okay, we're not given an initial condition here, and so what we should be able to do is unsubstitute everything. So this is y over x here, and multiply an x into everything. So in the end, we get y is equal to 1/4 x plus cx squared. And that is answer choice B for 3. And it's correct. Question 4, let y be the solution to this following equation. So this is a Bernoulli equation. These seem to come up more often in this class than they do in MA 266, but we just have a nice easy equation. Well, it's actually not too easy to remember, but I'll just lay it out for you. So a Bernoulli equation is one in the form y prime plus p of x y is equal to q of x times y to the nth power. And what we can do is apply a substitution where v is equal to y to the 1 minus nth power, and that will allow us to rewrite our equation as v prime plus 1 minus n times p of x times v is equal to 1 minus n times q of x. And I'm not going to go into why this entire substitution works. I think it's more time efficient for your exams if you don't know how to do Bernoulli equations right now, to just try to commit this equation to memory. It's really not too much in the end, given that later on, actually I don't think, not in this exam, but things like the equation for variation of parameters and even reduction of order are pretty hefty compared to this thing. So it'll probably be just a good thing to commit to memory. But let's try to apply that for this particular case. So in order for us to get our p of x, our q of x, and our y to the n, we see that the coefficient on y prime has to be 1. So let's divide this t squared out. We will have y prime plus 4 over t times y is equal to, moving this y cubed over, 1 over t squared y cubed. So we see that n is equal to 3. We have y to the third and y to the n here. Those have to match up. And then our p of x is just our coefficient in terms of t on our y. So that's 4 over t. And our q of x is 1 over t squared. So let's go down here and replace everything. We have v prime plus 1 minus n, 1 minus 3, that'll give us negative 2 times p of x, where p of x is 4 over t, so we have minus 8 over t times v is equal to minus 2 times q over t, minus 2 times q of x. Oh wait, we're dealing with, that's what it is. This equation is all in terms of x. I gotta fix that, or that's gonna really bug me. T. Okay. We have negative 2 over t squared over there. And now this is a first order linear equation, and we can just apply integrating factor. So this guy right here will be our p of t term, negative 8 over t, and our integrating factor rho of t is e to the integral of p of t, so negative 8 over t dt. This gives us e to the negative 8 ln t. We don't care about the plus c, and so we can write this as t to the negative 8th power. Then integrating factor tells us that our solution, which in this case is v of t, because we still haven't unsubstituted, v of t is equal to 1 over rho of t, so we will have t to the 8th power, multiplied by the integral of p of t, don't listen to me. It's equal to, I'll just write this, I don't do this often enough. So in general, the solution for integrating factor y of t is equal to 1 over rho of t times the integral of rho of t times q of t dt. So there's your general equation. So our rho of t is t to the negative 8th, and our q of t is, in this case, it's not this q of t we have written over here, it's this q of t, which is negative 2 over t squared. So what do we get? We get minus 2 t to the negative 10th dt. Okay, our powers are getting a little high in here, which is slightly concerning, but hopefully this all works out. We'll see that v of t is equal to t to the 8th multiplied by what will this be? Negative 2 over 9 t to the negative 9th? No, it'll be positive 2 over 9 t to the negative 9th. Yep, that works out. Plus c. Okay, so we are essentially done. All we have to do now is undo our substitution. The original substitution we made was v is equal to y to the 1 minus nth power. So that is v is equal to y to the 1 minus 3, because n was 3, so this is y to the negative 2nd power. So we can replace that over here, y to the negative second power, and let's write this as 1 over y squared, and we can undo this by raising each side. Well, we'll have to flip the numerator and the denominator of each side, so we will have y squared is equal to 1 over t to the 8th times 2 over 9 t to the negative 9th plus c, and then we'll take the square root and stick a plus or minus on that right there. And since we see that our initial condition gives us a positive number, so when we plug in some t, we get a positive y out, we can get rid of the negative and we're just left with the positive side of that square root. So if we've done everything correctly, we should be able to plug in that initial condition and solve for c. So we get 3 over root 2 is equal to the square root of 1 over 1 times 2 over 9 plus c. Ooh, this is a little ugly. I hope I've done everything correct up to this point. Let's square both sides. So we will get 9 over 2 down here. And what can we do? What can we do here? Well, let's make this 2 over 9, and we can flip the numerator and the denominator over there. And okay, that works out pretty nicely. C is equal to 0. C equals 0. So we can just get rid of that in there. That seems to be a good indication that we've been doing things right up until this point. Let's plug in y at 2 and see if we get something that makes sense. Y at 2 is equal to the square root of 1 over 2 to the 8th. 2 to the 8th times 2 to the negative 9th is just 1. Okay, we have 2 to the 8th times 2 to the negative 9th times 2 over 9. So this gives us 2 to the negative first power, which is just 1/2. 1/2 times 1 over 9. So our answer should be D, but 1/2 times 2 over 9 will give us 1 over 9 down here. 1 over 1 over 9 gives us 9. This is 3. So 4, after all of that, is D. Wow, that's kind of a brutal problem. Not gonna lie about that. Okay. Yeesh. Question 5. We have our matrix A right here. We are trying to figure out which collection of vectors is linearly independent. So whichever of these column vectors, or they could be even talking about row vectors. Yeah, here, the column vectors of A transpose, that would be the row vectors. So whichever ones of these are linearly independent are columns or rows that correspond to pivot columns or pivot rows in the reduced echelon form of this matrix. So 1, 4, 7, 10, 2, 5, 8, 11, 3, 6, 9, 12. If we row reduce this, we should be able to pretty much just figure this out by inspection. So let's subtract 2 row 1s from row 2. We get negative 3 here, minus 14 gives us negative 6. Minus 20 gives us negative 9. We can turn this into a 1, 2, 3. Now what? Let's subtract 3 row 1s from row 3. That gives us a 0 here. Minus 12 is negative 6. Minus 9 minus 21. I'm incredibly bad at this. 9 minus 21, that should be negative 12. And then 12 minus 30 would be, okay, when I record these things, the pressure gets to me in very weird ways, and it usually affects my addition and subtraction. So I'm literally doing this, 12 minus 30. Yep, there we go, negative 18. That's what I would have expected there too, because that allows us to use row 2 to set row 3 to all zeros, because what we can do is simplify this down to 1, 2, 3, and then subtract row 2 from it, giving us 0, 0, 0. So we see we have leading terms in our echelon form in our first column and our second column. So these two columns are linearly independent, and therefore E is our solution for 5. 6, we have a salt tank problem here. Our equation every single time for this is dq dt plus r0 over v of t times q is equal to ri ci, where r0 is the rate of outflow from the tank, where v of t is the volume of the tank as a function of time, ri is the rate of inflow of a solution into the tank, and ci is the concentration of that inflow mixture. So we're told that a tank contains a mixture of 1 meter cubed of water and 8 grams of salt. So that means that Q0 is equal to 8. That's our initial amount of salt in the tank. Water containing a salt concentration of 4 grams per meter cubed, so that's our concentration, 4, flows into the tank at a rate of 1/4 meter cubed per minute. So that's our rate of inflow, 1/4. And so we can simplify that side down to 1. And the mixture in the tank flows out at the same rate. So that means our rate of outflow is also 1/4. And that means that we can plug in our v of t as well, because originally we have 1 meter cubed of water, and we have water flowing in and out at the same rate, so that's never going to change as time goes on. That will just be 1. So we can simplify this down to 1/4 there. Okay, we're looking for how much time needs to pass until we will have 5 grams of salt in the tank. And really what we can do here is integrating factor. So if P of t is just this term here, 1/4, then rho of t is e to the integral of P of t. That gives us e to the 1/4 t, and we can write our solution, which is Q of t is equal to 1 over rho of t, our integrating factor, so e to the negative 1/4 t times the integral of rho of t times Q of t, where Q of t is just this right-hand side term. So e to the 1/4 t dt. So what are we going to get here? Well, Q of t will be equal to e to the negative 1/4 t multiplied by 4 e to the 1/4 t plus c. And we could, and we will actually have to simplify this out a little bit more, but let's solve for our initial condition first. Q at 0 is equal to 8. So 8 is equal to 1 times 4 plus c. So c is 4 in order to make that work. Now finally, we are looking for the time at which we have 5 grams of salt left in our tank, so we can plug in 5 for Q of t and solve for t. Distributing this e to the negative 1/4 t, we get 4 plus 4 e to the negative 1/4 t. We can subtract this 4, divide by 4, and I'll rewrite this a little nicer, e to the negative 1/4 t, and we can take the natural log. We can take the natural log of both sides, and I'm not seeing any logs of 1/4 there. Maybe that is an issue. Is the answer C? Yeah, the answer is C. Did I miss something? Did I miss something silly up here? No, don't think I did. Well, let's just keep solving, but I think we messed up something really minor. Okay, because we divide by 4, and then we take the natural log, and we have the natural log of 1/4 is equal to negative 1/4 times t. Yeah, that is an issue. One, we're getting a negative time, and we're also getting the wrong thing. the wrong thing in here. Although, is that a property of logs that I'm just too old to remember? Because we have -4. Does the negative log of this thing, will this flip this to a 4? I am not sure, but I'm going to go look that up and cut the video, and we will know. Okay, so that is in fact a property of natural logs that I'd completely forgotten, although it does kind of make sense when you think about it, that we can remove this negative sign and turn this into a 4 instead of a 1/4, and that will be our solution there. So our solution, in fact, is C for number 6, but I think it's a little bit rude of them to throw in that kind of almost calc or pre-calc fact in there that there's no way I remember that, but whatever. Okay, number 7. Given these vectors, for what value of h is b in the span of v1 and v2? Well, we can interpret b, this vector, being in the span of the first two, meaning that there is some linear combination of this vector and this vector that will give us our vector b. And we can solve for that by just putting everything into a matrix together. -1, 4, 1, 3, 4, 5, and really it should be an augmented matrix and with 1, h, and 1 on the other side, because we're finding the linear combination of these guys that produces this. Okay, let's add 4 row 1s to row 2. We get 0 plus 12 is 16 plus 4 there. Let's add 1 row 1 to row 3. 0, 8, 2. So we can turn this into 4 and 1 and subtract 4 row 2s from, 4 row 3s from row 2. That gives us a 0 here and an h there. So what does this mean? What does this mean for us? Well, if h is equal to, that is it. Yeah, if h is equal to 0, what happens? If h is equal to 0, because otherwise, if h isn't 0, if h is 1, or, well, if h is anything other than 0, then we have an inconsistent system here. But if h is equal to 0, then not only is this system consistent, but if we, let's see, I'll turn this into a 1 and this into a 1/4, and then let's subtract, make this 4 over 4, subtract 3 row 3s from row 1, we get a 0 here, and a 1/4 here. We'll flip that sign. We see that this is our linear combination that works. If we take -1/4 multiplied by our first vector, -1, 4, 1, and we add it to 1/4 times our second vector, 3, 4, 5, we should get our third vector, b, which is 1, 0, 1. Let's make sure that that does work out. So this will give us what? We have 1/4 plus 3/4, that's 1. -1/4 plus 1/4 is 0. -1/4 plus 5/4 is 1. So this checks out, and there you go. For no other values of h will this work out, because the system will be inconsistent. So 7 is A. 8. Consider this linear system. Which of the following gives the solutions to this system in parametric form? So immediately, if you see some crappy block like this, turn it into an augmented matrix. So we have 1x1 plus 0x2 plus 1x3 is equal to 2. We have 1, 2, -1, 4, and 3, 1, 2, 3, 1, 2, 7. I'll duplicate this thing, and we can row reduce to find our solutions. So let's subtract 1 row 1 from row 2. We get 0, -2, 2. We can turn this into 1, -1, 1. And then we're subtracting 3 row 1s from row 3. 0, -1, 1. Now, since row 2 and row 3 are equal, we can use row 2 to set row 3 to all zeros, and we are good to go. So the thing that you have to do here is to not only take into account this solution here, now that we have things in reduced echelon form over here, but you also have to take into account our free variable. Our free variable is x3 here. So if we write out these equations, we see that x1 plus x3 is equal to 2, and I'll subtract that free variable over, that x2 is equal to 1 plus x3, and that x3 is free. So if we're writing our solution will end up being 2, 1, 0, just the constants that we have in here, plus some variable, they use t, multiplied by negative 1, 1, 1, where negative 1 x3 is equal to x1, like we see in this equation. 1 x3 is equal to x2 in this equation, and x3 is just equal to 1 of itself at all times. So that's why we have that down there. So that gives us answer choice A, and we need a variable here because it's a free variable, because x3 is a free variable, we need to be able to fully control it. So to have like a little slider that we can move between negative infinity to infinity in order to get all of those potential solutions. So A is our answer for 8. Question 9, find all the values of h for which the linear system has no solutions. Again, it is augmented matrix time. 1, 3, 1, 4, 1, negative 1, 1, 5, 3, 1, h, negative 1. Okay, great. Let's subtract 1 row 2 from row 1. That gives us a 0 here, a 4 here, a 0 here, and we are subtracting, so this becomes a negative 1. Let's subtract 3 row 2's from row 3. We get a 0 here, a 4 here, an h minus 3 there, and I said we're subtracting. See, I lose track of this sometimes. We gotta backtrack. It's late at night. We're subtracting 3 row 2's from row 3. So negative minus 3 there, plus 3 here is 4, minus 3 here, and minus 15, so negative 16 there. Okay, looks good. Let's subtract subtracting row 1 from row 3. That will subtract 4 here and add 1, so we end up with negative 15 right there. So when will this system have no solutions? Well, we're dealing with a system with no solutions when we have our left side, blah, blah, blah. We can have as many variables that are 0 on the left side as we want, but if we have something that is not equal to 0 on the right-hand side, then what that's saying is 0 of everything, add that all together, is equal to something that's not 0, which doesn't make sense. It's inconsistent, and that's no good. So if h is equal to 3, what happens here? We get a 0. So we have 0x1 plus 0x2 plus 0x3. That can't be equal to anything other than 0, but it's saying that it's equal to negative 15. So h is equal to 3 is no good for us. So D is correct for number 9. Question 10, we have a transformation, linear transformation from R2 to R3, and we know these things about it. We know that the transformation of 1, 1 gives us that output vector, and the transformation of 1, 0 gives us that output vector. But we have two properties of linear transformations that will allow us to solve this very easily. The transformation of x1 plus x2, where x1 and x2 are just two arbitrary input vectors, is equal to the transformation of x1 plus the transformation of x2. Additionally, some constant times the transformation of x is equal to the transformation of that constant times x. So what this implies is that we can find the linear combination of this input vector and this input vector that produce this input vector that we're looking for the output of, and then all we have to do is take that same linear combination of these two output vectors, and we are good to go. So we're solving the augmented system 1, 1, 1, 0, 3, 4, finding the linear combination of these two that produces that. Let's subtract row 2 from row 1, and there we go. We see that 4 of this first input, so 4 times 1, 1, and this is all getting transformed. 4 times 1, 1 minus 1 times our second input vector, 1, 0. This will give us what we want, but instead of having to compute all this, we can just take, like I said, the same linear combination of these two output vectors. So we want 4 of our first one, that will be 4, 8, 12, and then we're adding -1 of our second one, -4, -5, -6. That gives us 0, 3, 6. So E is our answer for 10. 11, ooh, it's a big one. Let A be a 6 by 5 matrix. So we have 6 rows, 5 columns. And I'll actually draw that a little bit more to scale so that we really, we can't forget that our matrix is taller than it is wide. And B is the reduced row echelon form of A. Which of the following statements are true? If B has 5 pivots, then the column vectors of A are always linearly independent. So if B has 5 pivots, we know that the rank of A is equal to 5. Rank A is equal to 5. And what that implies is, yeah, that we have a pivot position in every single one of our columns. That means that all of our columns are linearly independent because they all have, independent control over one dimension of our output space that none of the other columns do, if that helps you think about it a little bit. But so this would be true since we only have 5 columns and we have 5 pivots. Yep, they're all linearly independent. If B only has 4 pivot columns though, then are the column vectors of A always linearly dependent? Well, yes, they must be. If we only have 4, it doesn't matter how you slice it, we still have a 5th vector without a pivot in it, no pivot in that 5th column, and that means that by definition, that set of vectors, the columns of A, are linearly dependent. So this is, yes, also true. What about 3? If B has only 2 leading ones, we can just read that as 2 pivots, so rank of 2 in A. Then AX equals B always has infinitely many solutions where B is any vector in R6. So they're saying we have 2 pivots, but we can think about this geometrically instead. So B having 2 pivots means that its output in R6 will be 2-dimensional. So you can think of a plane, some arbitrary plane in R6. So because we are cramming, or sorry, we're fitting 5 dimensions into 6 dimensions when we do this transformation, AX equals B will not necessarily have infinitely many solutions because we're only outputting in 2 dimensions. So there are infinitely many vectors that you can choose in R6 where our transformation it does not have a defined output. So you can bring this back to kind of an R3 example. I'll just draw out a quick set of axes. If you had a transformation that outputs the xy plane in R3, and this transformation matrix would actually be 1, 0, 0, 0, 1, 0, 0, 0, 0. So we have the xy plane. This thing does have infinitely many solutions wherever it's defined, but there are infinitely many vectors that do not lie on that plane, so there is no solution there instead of infinitely many. What about 4? If the entries of the last row of B are all 0, then AX equals 0 has some non-trivial solution. They're trying to be really sneaky here, so they're saying that our matrix has the form with 5 pivots, but then in the last row, we have all zeros. But what you have to remember is that since we only have 5 columns, we only have x1, x2, x3, x4, and x5. And that's important because since we have 5 pivots, we know that each one of these variables has a pivot with it. And since we can also just apply the equation that rank plus nullity is equal to the number of columns our matrix has, we can replace these columns with 5. Our rank is still 5, and so the nullity must be 0, where nullity is just the dimension of our null space, where when nullity is equal to 0, ax equals 0 will only have the trivial solution, and so this is also false. So 1 and 2, B, is our answer for 11. And finally, 12, we have some matrices, A and B. We're trying to find the sum of the elements in the third column of A inverse multiplied by B. Let's find A inverse. That's equal to 1 over the determinant of A multiplied by this kind of thing. So if we denote the entries of A as A, B, C, D, then this bit of our inverse will be dA negative B negative C. And of course our determinant is just AD minus BC. AD minus BC gives us 1, so that whole thing will go away. And then flipping these around, we get 3, 1, negative B is negative 2, and negative C is negative 1. So there's our A inverse. Now we are multiplying this by B, which is 0, 3, 1, 4, 2, 5. This is a 2 by 2. This is a 2 by 3. That means we will get a 2 by 3 matrix as an output. And well, let's think about what we'll have to multiply together to get our third column in A. We'll get our first column by multiplying our first row of A by our first column of B, and then that'll give us this entry, and then multiplying the second column, the second row of A inverse by the first column of B will give us this entry. So if we switch this and multiply, or find the dot product really of these two, this row and this column, that will give us the first position that we're looking for, which is the 1, 3 position of our output matrix. And what will this be? This will be 6 minus 5, which is 1. And then for our second position, minus 4 plus 5, which is 1. So our answer is 2, which is C. Okay, this exam was relatively straightforward, except for a little, natural log craziness there, and a really kind of brutal Bernoulli equation thing. Yeah, but hopefully this was a little bit helpful for you, and have a nice day or night, whenever it is, morning, whatever.